everyone. As I just got introduced, my name is Mark. I'm standing in for one of my colleagues who was supposed to be giving this talk. This is the first time I think I'm giving a marketing talk, so I'll do my best to put my marketing hat on, but you may have to bear with me a little bit. So I first want to kind of introduce what Ayar Labs does and how we view our business and what we're planning to build and sell. And so here, what we like to say is Ayar Labs designs and sells optical I/O, and we, for short, call that OIO. So, really, our vision here is that the I/O issues that compute SoCs are facing kind of such severe problems that we have to force a transition to a new kind of densely integrated optical I/O that integrates very closely to SoC chips and ASICs. And brings optical communications directly to the SoC package. And so, very kind of simply put, we say that our solution is delivered as a CMOS-based electronic photonic chiplet and using a CWWDM laser light source. And I'll be talking about both of those things in a bit of detail during this talk. So let's start with the problem statement, and this is a little bit of a technical slide, but on the left side, this is probably the simplest way to understand where the problem is emerging from. And what it shows is a trend in power consumption in compute packages over the last several decades. So that kind of light blue line is the total power per package and how that's grown over several decades. Now, the interesting thing is the purple line shows how the power consumption inside of compute packages has grown the proportion of power that's going towards off-chip or off-package I/O. And the problem is that these two lines are obviously on a collision course for sometime about right now. And researchers, including myself, kind of recognized this more than a decade ago. And this trend was predicted to hit roughly around 2020, at least in kind of R&D. And of course, products following that would start having severe problems. So we started working on building a new kind of technology from the ground up that was a combination of high-performance electronics and high-speed CMOS electronics, as well as a new generation of silicon photonics and photonic devices. And also thinking about the overall optical architectures that we need to build using this kind of approach to really solve this problem. Now, the right side of the chart is a little bit harder to understand, but it shows the kind of severity of the issue that's happening. And on the y-axis is a figure of merit for I/O, and it's a combination of bandwidth density and energy efficiency. And the x-axis is a logarithmic scale of distance. And what this shows is, we kind of think about basically three regimes of I/O in computing systems that we're targeting. The first regime is in package. So this is communications that are happening inside of a CPU package, let's say up to the kind of tens of millimeters of distance. And at that distance, electrical signaling is still incredibly efficient, very dense, very energy efficient. Very hard to beat over those distances. But then you go to onboard distances, which range, let's say, in the hundreds of millimeters to getting into centimeters, maybe up to a meter. And the interesting thing is this figure of merit has already dropped off by more than an order of magnitude once you go to onboard distances. And as you go farther than that, if you want to go board to board, then today that's typically being done either through passive electrical cables or more and more through optical cables that are plugging into the faceplate of these servers. So these are kind of faceplate pluggable optical transceivers. Now, once you get to that regime, of course, the beauty is optics kind of flattens out the distance penalty, so you no longer have a severe penalty versus distance. But you've paid a more than 10,000x penalty with this figure of merit to get to those optical solutions. So the way we kind of view this problem is that we need to be building the new solutions that target and approach the efficiency of in-package electrical communications, and we integrate our optics into that kind of distance regime, but now we do the electrical-optical conversion within a few millimeters of where the high bandwidth electrical signals are actually being generated, and we then kind of break the bandwidth distance trade-off. So that kind of light blue box in the upper right shows the range of distances and figures of merit that we're targeting with our technology and in our product roadmap. So to touch on a few market verticals that we're going after, and some of these kind of mirror the previous talk, and I'd agree with some of the kind of financial numbers that were put on these verticals. Each one of these is very large. Exactly how large, of course, you could argue about and debate, but each one of them is a multi-billion-dollar market opportunity. And we group them into basically four kind of key verticals where we look at how our products fit into those verticals. There's the cloud, and really in the cloud, the value proposition is being driven by things like disaggregated architectures, wanting to kind of break away from the standard two-socket CPU architecture where every single server has its own encapsulated compute system, and really go into thinking about pools of resources where we can have a pool of compute, we can have a pool of memory, pools of storage, and also be able to dynamically allocate compute resources to memory resources in a kind of configure time fashion. This allows data centers to much more effectively utilize their hardware. If you've gone to some of the cloud talks from the hyperscalers, Microsoft, Facebook, Google, there's one example of the issues that they face here is pulls large portions of their memory that they actually can't access. They have to over-provision the amount of memory that they purchase, but if you actually go look at how much of their DRAM is being utilized, it ends up being small fractions. So they view it as a kind of stranded resource problem to where they're over-purchasing various hardware to size up for kind of max load type of jobs, and they would much rather have a flexible architecture that they can kind of reconfigure to more optimally run their applications. In AI and HPC, we're seeing this, and I've got a talk over in a workshop in about an hour that I'll talk more about this, but there's kind of a space race happening, or an arms race happening in AI and HPC, to where a lot of it is being driven by the hyperscalers and new companies, kind of such as OpenAI, who are driving what you can do with machine learning. But all of them are looking at kind of building larger scale-out systems. They really want to be able to connect many, let's say, hundreds to thousands of compute nodes together in a high performance enough fabric that allows you to treat that system as a singular logical entity. And the machine learning algorithms can easily scale in performance if you can do that. Now, the reason they can't today is because they don't have an electrical I/O technology that can scale to those kind of connections. And the optical technologies that exist today in pluggable transceivers and kind of Ethernet roadmaps are not nearly bandwidth dense enough or energy efficient enough. And there are other elements that come into play, such as latency. If you really kind of go insert optics in between compute and memory, or compute and compute, latency becomes a really big deal. 5G connectivity, and I'd kind of include 6G in that as well. There are ideas around just what you can do in disaggregated base stations, but the big one is also how do we get to digital beamforming? Digital beamforming and doing massive MIMO has been kind of a this pie in the sky dream of RF systems, and there's some key bottlenecks in today's systems as to why you can't do that. But once you have an optical I/O that's densely integrated directly next to the kind of both the RF sensors and the compute backends, you can build some disaggregated architectures that make digital beamforming much more viable. And lastly, in the intelligent edge, there's kind of that last category is kind of a catch-all collection of a variety of kind of applications that we're seeing throughout defense and some even consumer applications. So in the defense world, building kind of next generation RF systems, building phased array radar systems, some similarities with that kind of 5G, 6G category. And in there are even some consumer applications that we're seeing in augmented reality and virtual reality that are pushing massive amounts of bandwidth over relatively short distances. And they're finding that as they architect these solutions in kind of these next generation products, the electrical solutions can't really do it for them. So across this, we think we're looking at multiple tens of billions of dollars of market opportunity. Now, let's kind of start talking about what the technology is and where its value proposition comes from. At the core of it is trying to solve really the kind of fundamental problems that the SoCs are facing, which is that we need to escape massive amounts of bandwidth in small amounts of physical kind of shoreline distances and do that very power efficiently. And so one kind of picture to look at to just think about what our solution is bringing, and it's a little bit of I guess it's a marketing slide, but we build these optical chiplets that we call teraphi chiplets, so that's short for terabit phi, and one of those chiplets can support the same amount of bandwidth as 2,000 gigabit per second pluggable transceivers. And this is, a roughly accurate kind of size comparison here to just show the density is dramatically different. Now, once we have that density, and why do we need that density? Well, we're trying to match the kinds of performance and the densities that you have on actual SoCs. Because if we're going to build a chiplet technology that gets integrated a few hundred microns away from a high-performance SoC, then we need to be able to support the bandwidth density that's coming from that SoC. There's not really a clean way to fan out. If you fan out, then you're back to the electrical kind of distance problem. So you have to electrically support the edge bandwidth density of the SoC. And once we have this small chiplet, and we have a technology that allows us to build this chiplet, then we've already shown, in the upper left is a rendering of kind of an integration that we've done with a customer, and in the upper right is an actual picture of these chiplets and how they get integrated into an SoC. And the bottom right is just me holding one of these examples of two optical chiplets integrated into a state-of-the-art SoC package. And this particular one is a high-performance Intel FPGA. So, the chiplet integration platform, we're able to match the bandwidth density of these SoCs. We're able to do it in a power profile that's getting sub 5 picojoules per bit and with a roadmap down to 1 picojoule per bit. And this is all single-mode optical fiber. And we could go up to a couple of kilometers pretty easily if we want to. Although I'll say the majority of the demand for our technology right now is in the sub 100 meter, even sub 30 meter kind of distance. So let's kind of take a look at the overall optical architecture. I haven't talked about the laser much yet, so I'll start touching on the laser on this slide. One of the key things that we chose to do very early on was to disaggregate the laser source for multiple reasons. For economic reasons, for technical reasons, for performance reasons. We couldn't get to the densities and the efficiencies and the kinds of integration schemes that we wanted. For supply chain reasons, if you put the laser onto your chiplet, it really complicates the co-assembly with the host SoC. So what we've done is there are two main Ayar Labs elements to our architecture. There's the teraphi Optical IO chip, which I've kind of talked a little bit about already. It sits inside the same package as a host SoC. The second part is that we have a disaggregated light source, and we call that our supernova light source. And we're taking an approach to where you take that light source, you put it outside of the package, it's generating continuous wave light, and it's generating multiple ports of that light, each with multiple wavelengths of light. And so we've got this architecture kind of gives us the ability to really aggressively drive down some of the cost per, like the dollar per performance types of metrics, simply because we're aggregating as much as possible functionality onto the minimum pieces of hardware. And then we're doing things like amortizing the cost of these components over many ports of optical fibers and optical connections. And so the host SoC talks to the teraphi chip through the electrical I/O, and we have an electrical interface on our chip, and then we do the electrical to optical conversion on our chip. And we're using silicon microring technologies. So the core device in our chiplet is a microring, and that allows us to have a very efficient way to build WDM kind of architectures. Now, once we're in the fiber, like I said, it's single mode fiber, and we have the ability to go, kilometers of distance. Although we're focusing down in the kind of tens of centimeters to tens of meters distance. So here's kind of an overview of what the Terrify chip actually looks like and some of its key architectural features. Right now, the chip that we have as a product that we're delivering into early customers has what's called an AIB electrical interface on it. That is an electrical interface that has been open sourced by Intel, and it's one of the interfaces that's kind of supporting the emerging chiplet paradigm in the SoC world. And that's shown on the left side of this kind of block diagram. So we have a parallel electrical interface that comes in. We have a layer of digital logic that does the mapping between that electrical interface to our optical macros. And the kind of center of the chip here, with the alternating RxTX, RxTX, we call these optical macros, and they directly mapped onto what you would think of as a full duplex optical port. So in our first product, we have 8 optical ports, and it includes all of the electrical logic and all of the photonics other than the laser that you need for full duplex transmission. These are configurable up to 256 gigabits per second per port, so we end up with a just over 2 terabit per second chiplet. Now, importantly, we are targeting right now up to 32 gigabit per second NRZ signaling per wavelength. This allows us to have a very kind of clean communication channel that allows us to avoid things like aggressive forward error correction. Aggressive forward error correction ends up resulting in too much latency on the links to support some of the computing applications that we're targeting, compute to memory and compute to compute, which is a very different kind of constraint than the solutions designed for telecommunications, where you're not really as latency sensitive. And energy efficiency, like I said, this chiplet energy efficiency is kind of starting at around 5 picojoules per bit and really driving to less than 5 picojoules per bit as we progress down our roadmap in the coming years. So, what does this enable at an architectural level, and why are we excited about it, and why are some of our kind of initial customers and big customers excited about it? Well, it's really, we're going through a transition on how people think about building computing systems, especially in data center environments and where you need a lot of performance in some of your computing systems. And what this tries to show is, in the past, people were building monolithic, reticle limited, compute die. And your kind of compute socket was really limited to that die, or maybe a small collection of those die on a board. Now, what happened a few years ago, which was a big enabler for our inserting our technology into these roadmaps, was that people started breaking apart that monolithic die and actually building multiple silicon die, and this is where the chiplet paradigm came from. So they still build their digital core in the most advanced, TSMC node or Samsung, but they surround it with other die performing other functions from other process nodes. Two things: you're limited to around a few tens of billions of transistors in a kind of single package right now, but they're all operating in kind of one logical unit. And what we believe that Optical I/O is going to enable, and what we're kind of delivering our first products into right now to build, are future systems that actually allow you to think of an entire rack as your new compute node. So an entire rack is a kind of full, logically connected compute unit, and we can get into tens of trillions of transistors operating on the same or computing on the same problem at that point. So optical I/O and kind of breaking the bandwidth distance trade-off here allows you to really build larger physically distributed systems that are all connected and have kind of a pool of compute that's all working together on the same problem without having to traverse multiple tiers of networks. Now, there's a lot that we have to work on to really make this whole vision a reality. Of course, back in the academic days, when I first started working on this a little more than a decade ago, and working on some of the core device technologies, we were really starting in the upper left here, saying, hey, we have to start working on an underlying optical device technology that allows or that achieves a kind of performance that allows you to build very efficient architectures on top of. And so as I mentioned, we've chosen the silicon microring to build on top of. Now, once we have a microring device that we can operate in high speeds and use reliably, we build WDM architectures, and we built these monolithic or these microring devices into a monolithic CMOS process. So we kind of scale out what a combined electronic photonic configuration that allows us to build overall WDM systems rather than single devices. And we've partnered with high volume scalable manufacturers. We've one of the first strategic partnerships we made was with Global Foundries, and our wafers right now are running in their kind of flagship production CMOS foundry. It's public information that you can see that foundry runs 1,000 wafer starts a day. And so that capacity is and that the ability to kind of drive volume is key to driving the overall solution that we're trying to build. But we also have partnered throughout the OSAT ecosystem with high volume assembly companies and test companies, and we're really kind of pipe cleaning the entire supply chain for how you'll build a new generation of CMOS photonic solutions. And we had to kind of solve the advanced packaging challenges that arise with this. Now, our approach, and one of the reasons we chose to build a monolithic chiplet, is once you have a single chiplet, it dramatically simplifies integrating into the SoC package. You basically go flip chip assemble this die into the multi-chip packages in the same way that people are already doing advanced 2.5D integration today. The new thing is you have to attach fiber, so there is a kind of twist right at the end there. But the way that we've approached fiber attach and done it through partnership with our manufacturers doesn't disrupt the ability to really go assemble these multi-chip packages in high volume. And by having a single die is a huge advantage here. Now, we've also been working on disaggregation of these light sources. And lastly, we've been working with the ecosystem to try to build an ecosystem of suppliers and vendors and partners around these solutions. There are enough problems here to solve that we can't do it all ourselves, and we consider ourselves really a fabless design company. So we strongly depend on the right partnerships throughout the supply chain and ecosystem to build a path to market. One of those is the CWWDM MSA. We launched this at the beginning of 2019 in partnership with Chris Cole, and Chris Cole acts as the chair of this MSA. And this has been where we've been putting our efforts to start to standardize and define the specifications for the light sources. The key issue was that the lasers that are being built for the things like the Ethernet roadmaps, they don't allow you to build solutions that have the performance that are needed to attack this kind of optical I/O for computing market and opportunity. So we went and, along with kind of several promoter members, which includes most of the tier 1 laser manufacturers, we defined a specification, and you can go to this website, cwwdm.org, and that specification is public. You can download it right now. And we hit a major milestone at OFC this year where we ratified and published a 1.0 version of that specification. And I'll talk about more about it, but we've already demonstrated a 1.0 compliant laser module in partnership with MACOM. Now we have a great set of observers as well, and you'll note that in the observers it includes pretty much all, or between the observers and the promoters, we have all of the kind of high volume compute SoC players. So you have Intel, NVIDIA, AMD, and we've seen great traction with these companies as they're taking very seriously that their next generation solutions are going to need to start to adopting optical I/O very differently than how they do things today. So I'll fly by a few demonstrations here in my last few minutes to show where the technology is at. We hit a major milestone at OFC, and I presented some results in the post-deadline session at OFC this past year, to where we showed the end-to-end architecture working, and we showed a kind of live running 1 terabit per second link between two of our chiplets. And that used all 64 microrings per chiplet. So we had 8 ports running, and each port had 8 microrings on it. And we showed our laser source here on the left powering up that optical link. And so what you see here is on the left is the Supernova remote light source. That's kind of in an engineering test kit form factor. And then we had 2 of our Terrify test boards, Terrify number 1 and Terrify number 2. The remote light source is supplying all of the light fiber coupled into those chips. And then we have a full duplex link running between the 2 chips. And we were able to show that we could run this error-free, which is what's being shown in the kind of software in the background, where we're reading out telemetry and kind of link monitoring status. And we could run this natively error-free, which is better than 1E minus 12. So, yeah, that's okay, so here's some data on that demonstration. I won't spend too much time here. I'd point you to the OFC post-deadline paper if you want to see more. But this just kind of shows the measured data on all the key elements. The upper left shows all 8 output ports with 8 wavelengths per port. The upper right shows a optical spectrum that's been measured, or optical spectra that are measured on every output port of the transmitter. So this is a spectrum measured on the laser input to the transmitter output. The bottom left shows measured bathtub curves. So these are plots that show you what bit error rate is kind of running on the link. And this is, we ran this kind of live demonstrated in around OFC. And so you want to see wide margins in the middle of those plots, and every plot has wide margins on all channels. And in the bottom right is just a table that shows the aggregate data that was transmitted in these demonstrations, and confirms that there were no errors measured. So I think I'm close to out of time. How long do I have? A couple more minutes? 5 minutes. Okay, so a few conclusions and you know what we view the next steps are. Well, we think that kind of a new era of multi-terabit per second optical I/O is really has arrived, and we're delivering these solutions into early customer systems, and people are actually building some of those kind of rack scale systems that I mentioned earlier, and it's enabled by these optical I/O chiplets and overall architecture. I'd say there are exciting opportunities for the overall ecosystem to kind of align to a roadmap. You know, we think that there's a 15-year roadmap ahead of these devices and these products. But of course, we need to kind of move in lockstep in multiple points with a variety of ecosystem players to really manifest that roadmap. So we're excited to continue engaging with the overall ecosystem. And I mentioned that the CWWDM MSA is one of the main places. You know, we chose to start building standards around the laser source first, because that drives so much of the physical interfaces on how a customer actually adopts this into a system. So great progress there. I'd encourage everyone to go look at the 1.0 spec. You know, I'd say stay tuned. We are you know, really, we have some exciting kind of announcements on the progress on where we're at in integrating these solutions into customer systems, kind of planned and coming up throughout the rest of this year. So stay tuned on the progress from us. We think it's a really exciting time. So, okay, thank you. I'll take any questions.
Thank you, Mark. Guys, question. Let me give you the microphone.
Thank you very much for the talk. My question is a little specific. When you want to coupling the laser from the laser to your photonic circuits, then to the fiber, what specific technique do you use? Do you use the fused couplers, or do you use the geometry optics? What is the trigger to choose the coupling, and what's the important thing you're considering when coupling it?
Yeah, so we have done both vertical grading couplers and we've done edge coupling. And in production, we're heading to edge coupling. So we're going to be using edge coupling in our products. I think you asked what the most important elements are. So obviously the first one is insertion loss. Especially with these remote laser architectures, you have 3 optical interfaces to get through. And the insertion loss that you experience in the overall link budget, the largest single portion of that is the fiber to chip coupling. However, I'd say there's, and you can go look at multiple foundries now kind of showing this, we're kind of highly optimistic that kind of sub 2 dB per interface, approaching sub 1 dB per interface, is very possible with the solutions that we have right now. So, yeah, the other one would be, once you go to the edge couplers, it pretty much solves the bandwidth problem. Vertical grading couplers, one of their downsides are, of course, you have a fairly narrow bandwidth. Something like 30 nanometer 1 dB if you're matching to a 10 micron mode. But the edge couplers are much easier to make very large bandwidth, more than 100 nanometers of bandwidth, so you don't have a severe roll-off. Reflection is also one that we are concerned about, but we're using an isolator in our system, and so there's actually right now we're not very sensitive to reflection.
So a following question will be for the edge coupling. So how many channels can be make sure identical for the channels? So I say it's like 10 more channels there. So for the edge one.
So how many fibers are we using, or?
Yeah, it's like I say a fiber array there.
So yeah, we have right now we do 24 fiber arrays per edge per chiplet.
Okay, so for the edging coupling, can it make sure the identical of the different channels for the coupling efficiency and the loss?
Are you asking about the uniformity of the loss?
Yes.
Yeah, so I'd say I'd go back to saying 1 to 2 dB, with 2 dB is kind of an upper limit, we're highly optimistic that you'll have good statistical uniformity below 2 dB in production.
Right, thank you.
Yeah.
Any other questions? Yeah, over here.
So a question regarding the business model. Yeah, so you offer the Tera PHY, and you have to couple always with big guys like Intel, AMD, NVIDIA, right?
So our business model that we're really getting to is selling wafers of known good die. And so, you could, there may be kind of a product SKU from a big SoC company that adopts that into a product SKU. But we're also currently engaged with, I'd say, they're still very large companies, but not the big SoC companies. So the goal here would be that we're able to build a reference supply chain that can consume wafers of known good die and allow system integrators to kind of take over the actual module design. So our business model is to sell wafers.
And how do you deal with the interface? So one is using InfiniBand, the other is using AIB, the other is using NVLink. Who is compensating then this? Who is somehow making this a standard with your interface?
Yeah, so if you look at our roadmaps, right now we have an AIB interface, which is predominantly an Intel interface. But if you look at the roadmaps, we're aligning to really the dominant kind of PHYs that are coming through the standards in the compute world. So CXL, for example, and which is sitting on top of a PCIe physical layer. And I guess without getting too specific, our driving philosophy is to be protocol agnostic. So we don't. Even if you look at our chips right now, you could call us not a great marketing term, but you could call us a dumb PHY, where we really architect the solution to not have to build logic related to the protocol onto our chips. And so we think that there are ways to do that in our products that capture 90+% of the dominant PHYs on the market. And as long as we stay at the physical layer and remain protocol agnostic, then it's much easier to do that.
Thank you.
All right, we probably should go to the next talk, but let's thank the speaker again. Thank you, Mark.